All right. So there are some people back for more from last night. Well, it wasn't explained. It was thematically unfolded. We did talk a little bit about aliens last night. I said all the usual things I always say. So I think you've sat through it many a time. Nothing terribly new to add to all of that. There have been developments in the past year. The whole episode with the second Martian global surveyor, which went into orbit around Mars, and then was used to image the area of Mars called Cydonia, where the face on Mars supposedly resides. And as you probably know, if you care about all of this, the more high-resolution photographs seem to show a more normal landscape. The rhetoric spawned by the event was anything but normal. All positions hardened. This seems to be the new way it works, you know. Nothing sets a theory on the path to legitimacy like being disproved. It's almost a prerequisite. I got one piece of email at the height of that controversy where somebody said, well, of course it doesn't look like a face. Do you think the aliens would be fool enough to make it to look like something recognizable? So then I realized that the logic was no longer simply circular. It had acquired a sort of Mobius strip effect where, you know, the fact that it didn't look artificial had now become the strongest argument for its artificial nature, obviously. I'm interested in all of this. I'm more interested in the human personalities behind these things, because in the absence of certain knowledge about, you know, whether a given story someone's telling is true or not, it's become much more interesting to me to look at the personalities. And I was pretty confident that this was a good method. I still am confident that it's a good method, that if someone seems completely odd in other ways, then their commitment to a peculiar belief makes the belief suspect. But we tried to do a trialogue about this with Rupert and Ralph in Santa Cruz a few weeks ago, and they both just climbed all over me and said it was a terrible method and that it opened the door to witch hunts and ad hominem arguments and so forth and so on. And then Rupert's knockout argument was, most great discoveries have been made by people who couldn't stand the kind of scrutiny I was bringing to bear on people. That being nuts is no indication that you're not a genius or on the right track. That only time can decide. And that, you know, if you turn out to have enunciated a great truth, the fact that you thought your cat was an angel and that you talked to birds isn't going to be held against you. It's also, you know, one of the paradoxes that people often don't live by the philosophies they propound. Probably the most spectacular example of that is the English 17th century philosopher Jeremy Bentham, who is known as the founder of utilitarianism, and who proposed this thing he called the utile, which was to be a unit of worth that could be applied to work, art, objects, money. As a utilitarian, Bentham was a rationalist and an atheist, but when it came time to go to glory, he had himself mummified And now if you go to the Ashmolean Museum, just on the left, as you go in the front door of the side wing, there in a glass case, hat on head, cane in hand, is Jeremy Bentham in his mummified state, staring from a glass case. So he sort of had his cake and ate it too. So did Lenin, for that matter. I mean, for a dialectical materialist to allow an embalming and a shrine to be built to him is fairly peculiar. Let's see. We're still calling for topics, so it's not too late to... Well, no, that isn't one of them. That's been dealt with. That has a check after it. Anything but that. Someone asked me if I would talk a little bit about novelty theory, and to those of you who've heard it a zillion times, the stress will be on a little bit and on new things. There have been a couple of new developments in the past year. Let's see. Well, for one thing, I mean, revolutions in physics now come so quickly that we hardly have time to adjust to one before there's another. But there was a very startling, I guess I can't call it a revolution because not everybody has converted to the new truth, but there was an interesting development in physics over the past year, which is a number of very precise measurements were taken of nearby star clusters and their rates of velocity and dispersion. And it was discovered that there seems to be some kind of previously not only undetected but unsuspected force in the universe that was described in the popular press as an anti-gravitational force. What it is that, for the past 50 years or so, a question in astrophysics has been, is the universe expanding infinitely? Or is it going to reach a point of maximum gravitational expansion, and then gravitational expansion will reverse and it will fall back upon itself so that it will reach a maximum radius and then begin to fall back on itself? Well, these new measurements seem to indicate that once you subtract all the known physical forces in the universe, these star clusters there is a residuum of unexplained expansive velocity. In other words, the answer to the question, will the universe eventually cease expanding and fall back on itself? The answer now seems to be no, it never will. This may seem very technical and so forth, but it actually addresses some fairly basic questions. It means that if true, and the data is being second-checked and third-checked now, but if true, it means that the universe is not at its largest scale cyclical. It isn't like a great breathing creature that expands outward millions, billions of years, then collapses inward, then expands again. It seems to be a one-shot event that emerges from a singularity and spreads out forever. Well, I don't know how long forever is, but it's certainly a lot longer than 12 billion years, which is the current age of the universe, 12 to 15 billion years. So this seems to indicate that we're, in some sense, near the beginning of the life of the universe, and that whatever is going to happen in this universe, it's never going to be erased by cosmic backsliding. We talked a couple of nights ago, or maybe it was last night, about the second law of thermodynamics, which leads to entropy, heat death, breakdown of all structure, and dissipation of order. Apparently this universe will end like that, not in a recoalescence into a primal mass and a re-explosion and unfolding of its topology. So in a sense, that's both the death sentence on order and structure and morphology in the universe, or perhaps not. Perhaps the death sentence was the belief that a time would come when the galaxies would stop moving apart and would begin to move inward. And of course, in a situation like that, gas pressure and radiation and everything eventually would reach very critical levels, and structure would melt down into an enormous black hole. So in a sense, it clears the deck of this possibility that the universe will fall back upon itself into a simpler state. It means it either goes forward infinitely into entropy, or it goes forward infinitely into the overwhelming of entropy by this strange non-equilibrium phenomenon that we call organic life, and at its higher expression, mind. What does all this have to do with novelty theory? Well, basically it keeps novelty theory alive. In fact, it's a tremendous argument for it, because novelty theory has always said, as the universe ages, it becomes more and more complicated, period. It doesn't say as the universe ages, it becomes more and more complicated up unto a certain point, and then the process reverses as it falls back into a state of compression. This idea that it's interesting how this discovery took place. Discoveries take place in a number of ways. Usually in science, people are looking for something, and so a theory doesn't quite parse. There's a missing link, there's a hidden dimension, and people go looking for the answers, and then they either find them and don't find them. In this case, and some of the great and truly society reconstructing ideas have come this way. In this case, the results were completely unexpected, and nobody was looking for them. These measurements carried out on these star clusters were essentially to confirm existing theory. And when the data came back that these things were expanding, it was unexpected. No theory demanded it. And yet, it appears to be incontrovertibly true. Einstein, in the 30s, played around with this idea, and he produced at one point in his career what he called the cosmological constant, which was an expansion factor built into the universe at the axiomatic level. In other words, it was just given by God. It did not proceed from logical declension. And he fiddled around with this for 5 or 6 years, eventually abandoned it, described it as the biggest waste of time of his entire life, the biggest technical mistake he had ever been involved with. It now appears he was spot on. The cosmological constant is real. It is a constant. The value is close to what he calculated it to be. And it gives us a universe which, once born, expands forever. So that was a big support for novelty theory.
Why did Einstein abandon that?
It was felt that it was not necessary. In other words, it was felt that and it hypothesizes a force, you see, a force that in science fiction terms we would have to describe as anti-gravity. Under the influence of gravity, everything should eventually reach its gravitational limit. Under the attraction of everything else, it should then begin to fall backward. But this Einstein's constant puts enough of an oomph into the mix that the gravitational force is not sufficient to overcome it, and the universe will just continue to fly in all directions outward from its origin point forever. So in a way, though you probably didn't feel the speed bump, this little series of discoveries in physics last year, pretty much, if it holds up, if confirmed, settles a question that people have pondered for as long as people have been staring into campfires, which is the universe cyclical, as the Hindu cosmologies tend to believe, always larger and larger cycles, or is it a one-shot deal? And Western philosophy has always leaned toward the idea that while there may be cycles within cycles, that ultimately there is a cycle so large that it doesn't repeat. Ultimately, in this model, the universe is what's called a damped oscillation. And I think you can imagine what that is. A damped oscillation is when you pluck a string on a cello and then listen very carefully, it actually dies away. I mean, it fades, but eventually it is truly gone. That's a damped oscillation. So that's what the physics seems to have secured, that this is the kind of universe we're in. It raises ethical, I suppose, and philosophical questions in the sense that it means where we stand tonight, no one has ever been before. There aren't worlds which precede and follow history like bubbles in a glass of beer. It raises the stakes. Being becomes more important. The unique moment becomes truly unique. It's sort of in line with that, related to the same data set, if you want, which is the very large-scale physical universe. There was another development, not exactly development, but sort of the debate sharpened and clarified, and that is, as you probably know if you worry about astrophysics and the issues it grapples with, there is this big problem, probably the biggest unsolved problem in astrophysical modeling, is this question of what is called dark matter. What this is about is the universe behaves as though there's about 97% more of it than we can see. In other words, we look out into the starry universe and we see quasars and pulsars and stars and star clusters and galaxies and brown dwarfs and gas clouds and all these things. But when you add it all together, it's only 3% of what should be there for the universe to hang together the way that it does. And this problem has been, physicists have been aware of this problem for about 30 years. They call it the dark matter problem because they assume that the cohesiveness of the universe could only be because there are large amounts of unobserved matter that are contributing to the gravitational field of the large-scale cosmos. And then the question becomes, well, where is this dark matter? I mean, we build better and better telescopes. We look in more and more rarefied sections of the electromagnetic spectrum, but we don't see, the dark matter doesn't swim into view. one group is looking for these things called machos, which are massive haloed something objects. Anyway, I can't remember what the acronym stands for, but the concept is some big things that we've overlooked. The equivalent of brown dwarfs, which are larger than stars, larger than planets, and saying there must be billions of these things in the universe that we just don't see. The other school of astrophysics says, no, it's wrong to look for this in these massive objects. It's that the neutrino must have mass. Now, the neutrino is an interesting creature. It's one of these counterintuitive concepts which science depends on. In a single cubic centimeter of any amount of space or time, something like 10 high 14 neutrinos per second are moving through a cubic centimeter of space. How much is that? Well, 10 high 9 is a billion. So 10 high 14 is, 1,000 trillion neutrinos per second penetrating every cubic centimeter of space. And these things are hellishly difficult to detect. A neutrino can pass through the Earth and never encounter anything. The Earth is basically transparent to neutrinos. So trying to picture these things, of which there are more of them than anything else in the universe. So obviously if neutrinos had mass, even if it was a very slight amount of mass, there are so many of them that you could redo the arithmetic of reality and come up with a hell of a lot of previously undetected mass. Recently, an experiment which has been long running in Japan, and I forget where the other detector is, France or something like that. Anyway, in the bottom of these very deep mines, they build these tanks with tens of thousands of gallons of what is essentially cleaning fluid in them. And they believe that one in something like 10 high 20 neutrinos will actually, 1 in 10 high 20 will actually collide with an atom of this solvent liquid, and it produces a flash of blue light called Cherenkov radiation. This we don't have to understand, or at least I've managed to live without understanding what it is. But you can build a photo detector and detect these things. Well, there was a supernova burst and in the past year, and they detected the neutrino flux rose on the Japanese detector, and something like an eighth of a second later, the French detector also detected this wave of large numbers of neutrinos moving through the Earth. And for the first time, they were able to calculate the mass of the mass, but not enough to account for the dark matter that seems to be missing. Well, so what does all this have to do with novelty theory? Well, simply this. Maybe there is no missing mass. Maybe there is no dark matter. Maybe what's missing is a law or two. That would be a more elegant solution. And what I've always said about novelty theory, or one of its ideas that it kicks out quite naturally, is the idea that once something complicated exists, it has a kind of inertia for existence. You know, I've said once novelty is established, nature tenaciously maintains it. It doesn't easily give up and go back to a simpler state. So let's imagine now that we're looking at an enormous spiral galaxy comparable to M31 in Andromeda. And and the question you're asking yourself is, what keeps it together? 100 billion stars circling around a black hole. What keeps these stars from flinging themselves off into the great intergalactic night? Why does the thing hang together? Well, the orthodox answer is there must be missing matter that we can't see that is contributing and raising the amount of gravity in the system, and that's why it holds together. But I say no, it holds together simply because it is together. In other words, it has attained a dynamic status as an entity. Its sheer wish to maintain itself as it is sufficient to overcome the forces which are trying to fling it apart. What's interesting about this is if you could actually begin, if you believed this and you were a professional astrophysicist, you could actually begin to calculate your way toward a mathematical value for the universal constancy of the novelty factor. What you would do is you would calculate the visible mass of a galaxy, calculate the amount of force necessary to fling it apart, subtract one from the other, and what you have left over is apparently this hidden tendency to cohesiveness that's holding the thing together. Theoretically, you could do this on a human being, a human society, a population of atoms, a molecule, but of course these things are very, very difficult to separate from their background. With a spiral galaxy suspended in intergalactic space, you can actually make a fairly accurate estimate of how much mass you're looking at what its rotation speed is, at what the factors are, the tidal factors trying to tear it apart, and how great its attraction for itself would have to be to overcome that. So that was... See, if novelty theory is true, then on large scales, it would have to operate that way. We've always talked about it on tiny scales, either the scale of human history, a few tens of thousands of years, or on much smaller scales, atomic, molecular, and systems like that. But at the cosmic scale, you actually can begin to get a feeling for the mathematics of it. So those were the two areas in the past year that on the cosmic scale have contributed to strengthening novelty theory. The discovery of this apparently universally deep, repulsive force that is causing the universe to expand forever, to never retrace its steps. And then paradoxically, this strange force that favors the coherency of large structures and doesn't allow them to come apart, even when the gravity necessary to hold them together is absent.